Hi. Good afternoon, everyone. Thank you for coming. My name is Stefano. I'm a product manager at AWS. I work in the automated reasoning group. And presenting with me today is Byron, who's a distinguished scientist in our team. He's been working his whole life in the automated reasoning space. We're going to go through a few things today. Let me give you a bit of a structure for this session. I will start by telling you a little story that hopefully it's relatable of how we came up with the idea, what we tested, what we tried, where we failed. Then I'll introduce automated reasoning checks at a high level. I'll kind of try to give you our mental model, what we believe is important for this product. Then I will hand over to Byron. Byron will go deeper into what automated reasoning is, how it works, and why we believe it's so important. And it's a fantastic space. Then we'll take it back and we get to the practical bit. I'll show you how to get started with the feature, how it works. We'll show you a quick demo and hopefully leave you with some next steps you can follow to learn more. So let's get going right away so that we can keep some time at the end, hopefully, to answer your questions. How we got here is probably a common story. I don't think you'll fight me on this quote, which is 95% of CIO feel that generative AI is an important shift. It will improve customer support. It will improve productivity, right? This is the first thing I thought when I saw the first LLMs come out. And what happens, and I'm sure it happens the same in your organization, the leaders turn around and voluntold somebody, you go and tell me what our strategy should be with this exciting new technology. And the first thing I went off and did was try to understand large language models, how they work. I was not in the machine learning field, so it was new for me. Then I took everything I learned and I brought it back. I tried to educate my leaders. And finally, I got to the exciting bit for me, product manager, which was identify use cases. And this, for me, was a no-brainer. You can start with onboarding new employees. We can make it much cheaper if we can create a chatbot that knows all about our company policies and workflows. We can simplify customer support, no longer waiting on a website in a chatbot queue for somebody to answer. And if we go even further out, think about automating decisions. And I'm not talking about the simple, oh, you spend more than $50, therefore shipping is free. I'm talking about complex, ambiguous decisions, the kind of things that you just don't do in software. You forward to a human. And so once we identified these use cases, we started experimenting. And it was definitely, wow. I mean, I don't know about you, but I was blown away. I could just take a PDF, give it to this thing, and say, give me back a JSON of key value pairs of character names and their background. And it just worked, right? And so we got to build, and we built so fast. We built so many prototypes so quickly, and we decided to start pushing some of them towards production. And this is where you get a little bit more pedantic with your testing, and you get QA people involved. And what we found is that it worked, but it wasn't accurate. And I'm not talking about massive mistakes. LLMs are actually very good. Hallucinations are subtle. In this example, I just took a piece of text and I asked the LLM to condense it down to one sentence. And he did an amazing job at capturing the fact that our friendship is cemented on the fact that we love solving advent of code puzzles. Now, can you see the hallucination here? I'll give you a minute. Raise your hand when you spotted it. Yeah, quite a few. It's subtle. It's not a massive mistake, but when accuracy matters, when you're putting things in front of customers, it's not awesome if you call them by the wrong name. And so out of this, guess who's not going to production with their experiment? And so we go back and say, what can we do here? And by the way, we are not alone. You are not alone. Hallucinations are a top concern for the entire industry. They are the highest concern here. In fact, it's not just the highest. We are getting more concern year over year. From 2023 to 2024, we went from 50 to 59% of respondents saying, we got to solve hallucinations. Now, don't take me as an LLM detractor. I still love working with LLMs. I think the potential is there and it's huge. And I don't want to completely eliminate hallucinations. That's a desirable property for me. It's what makes LLM creative. It's what will eventually allow us to delegate ambiguous and complex decisions to LLM. And this kind of brings us to automated reasoning checks. We just really want them to be factually accurate. I want the creativity, but I want you to quote your facts correctly. The way we think about automated reasoning checks, and our priorities are three. Well, the first one is obvious. We want it to be accurate. We should be identifying factual claims, factual statement, and suggesting corrections that are good. We want it to be sound. Now, Byron has a formal definition for soundness. I'm not even going to try and tell you because I'm going to butcher it. So I'll give you just a simple version that I understand, and that is, we will not claim that something that is wrong is right. That is the cardinal sin. We'd rather say, we don't understand. We need more information than make a validity claim that is not true, if that makes sense. And finally, and I think possibly even more important, is transparency. It's explainability. Because we understand the structure of the knowledge, we can give you a mathematically provable explanation of why we believe something is valid or invalid. It's a chain of evidence, inference, evidence, inference. That is an auditable log you can save. When it works best is for what I would call factual knowledge. These are things that boil down to a yes, no, or always never answer. Things like your HR policies, your laws and regulations, and operational workflows. What is not well suited for are the qualitative use cases, like does the generated content match my marketing messaging best practices? Is not something we can validate. It's not likely to boil down to a yes, no, always, never. Probabilistic calculations, like you ask your LLM, hey, what are the chances of? And the LLM makes up something. That's not something you want automated reasoning for. And obviously qualitative descriptions, like describe S3 chatbot. This is not something that we can easily check with automated reasoning. But fortunately, we are part of Bedrock Guardrails. And in totality, the entire toolchain Bedrock Guardrails, I think, is the most comprehensive in the industry in what you can do. It covers all topics. It starts from preventing prompt injections and attacks against your applications. You can define topics that your LLM is not allowed to talk. Just literally give us a natural language description of the topic, and we'll try and block it. Same for specific words or harmful content. You can redact PIIs from prompts and output. And finally, using contextual grounding checks, another feature of Bedrock Guardrails, you can check that the response the LLM generated is consistent with the context it received. This is your RAG content that you fed it to generate the answer. So automated reasoning checks slots in here, and it helps you identify, correct, and explain the factual accuracy of LLM responses. So I think if you take all of these things together, you have an incredibly comprehensive toolkit to build responsible AI applications. Now, that hopefully is a little bit of high-level context. Now I'll hand over to Byron to tell you more about automated reasoning and talk you through how it works behind the scenes, so then we can get to the practical part.
Thank you, Steph. Yeah, so I'm going to try and tell you what is automated reasoning. Otherwise known as symbolic AI, goes by various other names, formal verification, and so on. So, you know, if we go back in the history books and look at the development of artificial intelligence, it goes back before the 50s, but the 50s were sort of a crucial time because the digital computer became commercially available, and so you know, researchers began looking at this problem with a lot of interest. So there was a very crucial moment. It was the 1956 artificial intelligence workshop was at Dartmouth College, and it was attended by folks from various disciplines. So you had cognitive scientists, you had logicians, you had Claude Shannon, people from a broad array of areas getting together and trying to figure out how we can use computers to create artificial intelligence. And out of that meeting brew a bunch of interesting ideas that are interlocking, that connect and can be used in kind of interesting ways. And so broadly speaking, the sort of pillars of that would be connectionist AI, probabilistic AI, and symbolic AI. So, connectionist AI is rooted in ideas from cognitive science. Probabilistic AI is rooted in ideas from Bayesian reasoning, and then symbolic AI is rooted in mathematical logic. And so these days, like that was quite a while ago. Over time, the terms have sort of slightly changed, and sort of people know these ideas as machine learning and automated reasoning. So that's with today's lingo. Now, one thing that's interesting is that, so let me sort of compare and contrast them slightly. So if you take a broad view of what machine learning is taking a whole bunch of data, so let's say a whole bunch of triangles, right? And it's computing a model that is hopefully predictive, right? So maybe somewhere deep in our model that we've computed over the large number of triangles, we've learned essentially the Pythagorean theorem that a squared plus b squared equals c squared when you have a right angle triangle, right? So that's where we're annotating a, b, and c. Those are the sides of the triangle. Or maybe we learn something slightly off, right? And so this is the sort of challenge with machine learning. You may take a whole bunch of data and you learn something that's not quite right, but maybe it's close enough, and maybe it's close enough for your application. So that's kind of the challenge of machine learning. And so then that's training, and then sort of inference or testing, or is in some sense the dual, right? We now have a model, and we deploy that model, and we use it to make predictions. We use that model to decide what things are. Like we can take images and recognize things in images, or we can generate data from that. But if you think about it, that formula describes an infinite set. There's an infinite set. There's an infinite, in fact, uncountable number of triangles that meet this constraint, right? So there's many triangles, and what reasoning is fundamentally is the act of talking accurately about all possible data simultaneously that a model can produce. So this model could be a program, it could be a representation of triangles, it could be, it's the thing that, it's the universe that we're talking over, right? Even when that's infinite or intractably large. So the Pythagorean theorem, for example, has been proved. It's been proved in a finite series of steps, even though its domain is over an infinite set of triangles, and it's impossible to enumerate all of those triangles and check that the Pythagorean theorem holds for each one of them. What's been very interesting, as I've been working in the space for 25 or more years, is that we're beginning to see these branches come back together because of the interest in the general public, the investor community, IT community, a whole bunch of folks are, because of generative AI, are really interested in the combinations of these techniques. And so that would typically these days be called neuro-symbolic AI. And that's driven by this kind of interesting trend. Hold up your hand if you know the Gartner hype curve idea. Okay, so I'd say about half the room. So the idea is, and you're going to see this kind of everywhere in tech, right? That new ideas are introduced. They're super exciting. People get really excited about them. Their ambition, their excitement often exceeds the actual capabilities of the technology. Then the technology doesn't do kind of everything they thought it should do. Then they get extremely disappointed. And so there's a period of time where the technology is kind of in the doghouse with the IT community, so to speak. And then over time, people begin to realize where it's good, where it's not good, how it can be combined. And so here at Gartner in the AI space is showing you where each of these technologies is kind of in the current hype curve. And so, the reason many of you have come to this talk today is because you're beginning to experience, it's like, okay, this technology doesn't do quite everything we thought it was going to do, right? There's hallucination. By the way, hallucination is good. That's creativity. But it applied to certain domains, incorrect answers turn out to be a problem. And not far behind are foundational models themselves, right? Is there a scaling wall? If we just pour more and more data into the training of these models, do they get better? And is there more data even to pour into these models? So we're as a community beginning to realize that maybe these technologies can't do everything, and then we're going to go through a period of huge disappointment, and then we'll go through a period where we figure out how to use these and in what cases to use these. And so what that's doing is that's driving an interest in this area of neuro-symbolic AI. And so symbolic reasoning, formal reasoning, logical reasoning, symbolic artificial intelligence, that word symbolic comes, the symbolic and neurosymbolic is formal logical reasoning. So I wanted to zoom into a bit more detail. I'm going to assume that you have enough material in your life about what machine learning is. So we won't go into that. We'll go into the automated reasoning part. And what I'm going to do is I'm going to show you an example. This is an example from a blog post I wrote 3 years ago, I think. It's called a Gentle Introduction to Automated Reasoning. I welcome you to go read it. But there's a couple of examples in the paper, in the blog post, but we'll just go through one here. And so what we're going to do is we're going to look at a small example. I'm actually going to give you a moment of awkward silence to think about it, so you can like stop listening to me and actually think about the code. And the question we're asking of this code is, could this loop run to infinity, right? So could this loop spin forever? Are there values for x and y such that this loop would not terminate? We're going to assume that the Python interpreter is acting correctly. We're going to assume that the underlying microprocessor and compute stack is operating correctly. And I'll remind you that these are integers, and in Python you can have, it's not fixed with integers. So I'll give you a moment to think about it. All right, what do you think? So hold up your hand if you think it guarantees termination. There is no way for this thing to run forever. And hold up your hand if you think this could spin forever. Okay? And hold up your hand if you don't know. There you go. Okay, good. So for those of you who determined that this program will always terminate, the steps you went through in your mind is reasoning. And so automated reasoning is essentially the algorithmic production of the thing that you did. So let's go through it. So it turns out that x greater than y will eventually fail, no matter what the starting values of x and y are. Okay, and the reason for that, and I use the word reason very intentionally, it's not accidental, is that the value of the function x minus y, so if we take the expression x minus y, that's essentially a function because we're taking a state of the computer program and then we're asking, oh, okay, what is the value of x and y in this current state? That function is always decreasing. On every iteration of the loop, it's decreasing. And when x minus y is positive, the condition x greater than y will be true, and when x minus y is negative, then x greater than y will be negative, or will be false. So thus, because that number is decreasing, x minus y is decreasing, then that means we are eventually going to hit the case where x is no longer greater than y, and thus that condition will fail. Now, why is x minus y always decreasing? Okay, well that's in part because y is always positive and constant. Okay, so why is x always positive and constant? Well, that's for two reasons. Reason number one, entering into the loop, so we call this the base case. In mathematical induction, we call this the base case. In the base case, y begins its life as positive. It's actually a condition of entry. We check that y is positive before we go into the loop. And the reason number two is that y is actually not touched at all by this loop. So thus, y is positive and stays positive throughout the loop. And so for those reasons, because x minus y is always decreasing, and I know that's true because whenever you take a positive value, like you take x and you decrease it by a positive value, x is going to be going down, and we know that y is constant, thus x minus y is always decreasing, and for that reason, we get the condition. And basically, automated reasoning is the algorithmic production of that kind of thinking. Is essentially what we're talking about. And notice that this cannot be exhaustively tested, right? It's not possible to enumerate all possible x and y. And if you limit yourself to 64-bit integers, so you say, okay, we're only worried about, yes, I know that there's sort of arbitrary precision, but like we're gonna only worry about a certain segment. The computational cost of doing that testing is absolutely enormous, right? So by just shifting a few symbols, and the word symbol is, I'm using that purposefully, by shifting a few symbols around, we're able to, in milliseconds, show something that can't be showed in many lifetimes, or in the case of if we're talking about infinite numbers, ever. So that's the magic of symbolic AI or automated reasoning. Okay, so now I'm going to give that same argument, but I'm going to go into a little bit more detail. This part of the talk is aimed at probably about a third of you in the audience where you're like, okay, cool, but like show me the details. And then probably a third of you are going to be like, I don't know what you're talking about. So I will be available to answer questions if you want to talk about it. If you get a little lost in the next section, it's okay. After this piece, we're going to talk about how Amazon's been using this technology. So bear with me for a moment. So what we're going to do is we're going to zoom into a little bit more detail. I'm going to tell you the same argument, but we're going to do it at the semantic layer. So on the left top is the code, and I've put the line numbers. And on the bottom right is in set theory, I've described the semantics. This is the meaning of the program. So this is a relation between pairs of states, and it describes all possible transitions. And so when programming language theorists think about programs, they think about the semantics of the program, and that is an infinite set of it's a graph representing all possible transitions between the program. It's very, very infinite, and this is the formulation that your average programming language theorist would think about. So what we're describing is R is a relation. A relation is a set of pairs of states. So we're going from a state to a state. We're representing a state as a function. So a state is a function from stacked variables to values, right? And then we're asking, okay, so we basically have 4 cases. So the first case is we're at the first line of the program. So I'm using the variable p for the program counter of the program, and we're saying we're at line 1, and in the state y is positive, right? So we're in the if statement, and y is positive, so we're going into the branch, and thus the next in the post state t. So this is the state we're going to. We're now in line 2. And the value of y stays the same. So the value of y in the post state t is the same as the value of y in the pre-state s, and similarly for x. Okay? And so we're basically doing the same thing. So this is the case where we don't go into the loop. So basically we go outside, we go to the bottom of the code, and the states and the values stay the same. And this is the interesting one. This is the one where we're saying, oh, we're in the loop now, so we're at line 2. And the value of x is greater than y in the programs in the pre-state, and then in the post-state we're staying in the loop, so the program counter is still pointing to line 2, and now the value of y stays the same, but the value of x changes. So the new value of x in the post-state t is equal to the value of x in the pre-state s minus the value of y in the pre-state s. Okay, great. So the meaning and the text, that's the sort of crucial bit. Okay, and then, so now we can translate this question of does this program run forever to well-foundedness of relations, which is a concept, a well-known concept in set theory. And so what that's saying is if we take R and we begin applying it to states, right? We say, oh, we have this sequence of states and we apply R to it. If we keep conjoining R, eventually that conjunction of R is going to fail. So we're going to say it's not possible to take a transition. And that allows us now to formalize this a bit more. So let's go through that reasoning I did before, but we'll do it now in the set theory. So I said, y is positive and constant. We're going to ignore constant for a moment. That'll come back. And here's the proof by induction. So here's the case where we say, like reason 1, y is positive at the loop entry. So here we're saying that in formal logic, right? We're saying, oh, look, in the post state, y is positive. And that's under the condition that we weren't in the loop before. We've gone into the loop, and we've taken a transition through the program's transition relation, right? And thus y is positive. And similarly for reason 2, right? Here we're saying if y is positive in the pre-state, then y is positive in the post-state. And that again is assuming we're in the loop, we're staying in the loop, and we're taking a transition through the program. And the relation is defined below. And then I have one other thing. So here's the constant. So again, it has a very similar flavor. We're saying, in the pre-state and the post-state, y is positive under the assumption that that's on the left-hand side of the implication. Why am I telling you all this? I'm telling you this because there are tools that can take these formulae and answer them completely automatically. They're called SMT, Satisfiability Modulo Theory Solvers. We use them a lot in Amazon. I'll tell you about, we're going to talk a little bit more about how we use them. And these tools are off-the-shelf tools. We have internal services that use them in AWS, and this is how you can reason about programs. Symbolic AI. All All right, and the reasoning over the infinite. So these formulae are saying for all possible states, those are infinite sets. So it's an infinite possible set of states S, an infinite number of set of states T, and so on. So that's symbolic AI. And we can do the similar thing for X minus Y. I won't go into a lot of the details, but we're basically using this formula that we proved by induction now to show the decreasing. And then there's a whole lot of other steps to sort of combine it all up. So now I'm able to make an argument that this program terminates that's well-founded by bridging that to the set of integers and together with greater than, which is a well-founded relation, and then every sub-relation of a well-founded relation is itself well-founded, and thus we're done. So that's the part where I assumed I would lose a few people in the audience, but there are certain members of the audience that will explain things too. So now let's reset and go back to kind of how Amazon has been using this. So we've been using this technology for 10 plus years. It's all over. So for customers have access to automated reasoning. There are some of the managed config rules use automated reasoning. Inspector uses automated reasoning. VPC reachability analyzer is based on automated reasoning. S3 block public access uses automated reasoning. IAM access analyzer uses automated reasoning. And then we do a proof. We use this technology to prove the correctness of a lot of our programs that we use within AWS. And some of that is open source. So encryption SDK is an example. There's uses of differential privacy in AWS, and that code and the theory has been proved correct using Symbolic AI. And then also the cryptographic foundations of AWS. Much of that is open sourced. So for example, S2N is our TLS implementation. AWS LC, that's the libcrypto like library that we use within AWS, and we use these techniques. And then furthermore, if you look at all AWS services are in some way touched by automated reasoning, right? And so I'll give you an example. There's a very nice talk from Reinforce, the security conference from AWS, where they talk about the recent proof of the policy interpreter in AWS. So AWS gets called, approximately 2 billion times per second. Every time you call AWS, there's a principal, an action, and a resource. The AWS grabs all of the relevant resources to the principal and to the resource, and then we make a policy decision, right? And that policy interpreter decides yes or no, should we take the action or not? And that code has been recently proved correct, and we deployed it, and it turns out it's actually remarkably faster. And what did we prove with that code? Well, it's actually based on IAM Access Analyzer. So I put up to represent IAM Access Analyzer, I have a picture of the console screenshot, so that the semantics of the policy language that we use in AWS is the basis of what we proved of the code. So we're showing that the code correctly respects the semantics that we use when analyzing your properties. And we do similar work for S3. For example, I saw Werner mention this in our strong consistency work. We do reasoning about the virtualization stack. And then we reason about networks, we reason about cryptography, we reason about virtualization, we reason about storage. And because all of AWS is built on those foundations, in a sense, every AWS service is in some way touched by automated reasoning. Okay, so I hope that was helpful. I'm happy to take questions afterwards, and I'm going to hand it back to Steph.
Thank you, Byron. All right, now hopefully you have some context and you see why we think there's huge potential in automated reasoning. So let's get into the practical bit. How do you get started with automated reasoning checks? I'm going to use a practical example. I'm going to take the use cases we discussed at the beginning of the session. Onboarding new employees, customer support, etc. We're going to take an easy one, onboarding new employees. I probably don't need to tell you this, but we'll go over it. It's expensive to onboard new employees, right? You either send them off for training somewhere, which means they're not productive, or you temporarily reduce the productivity of the entire team as they teach the new person. It would be awesome if we could create a chatbot that knows all about your corporate policies and can quote them accurately. This way, you make the new person productive instantly. Getting started with automated reasoning checks is a 3-step process. The first one is to create what we call an automated reasoning policy. That is a structured mathematical representation of your knowledge. Byron talked about how we create a logical model of how IAM works to prove that the authorization is correct. That's what you're doing here. You're taking your documents, your knowledge, and creating that logical model. Once you have that model, you can configure Bedrock Guardrails to use the automated reasoning policy to validate incoming questions and answers. And I mean, step number 3 is the obvious profit. Just use it at inference time to validate your Q&A. Let's go through a practical example here. I've taken a leave of absence policy. This is a pretty standard HR policy. You know, you have to be greater than senior, you have to have 10 years of tenure, and then you're allowed to take leave of absence. When you upload this document, what Bedrock does is identify important concepts in the document. These are nouns that will likely become variables in a schema that represent this knowledge. This is the first thing we do. Once we have that, then we go over the document and we pick up individual rules that operate over those variables in the schema. And we translate those to formal logic that notation Byron has shown. Here I'm simplifying it. It is effectively a decision tree that we're constructing. The user of the Bedrock console can use our tool to refine this policy. It's possible that we misunderstood one of the rules, or it's also possible that it turns out one of the rules is ambiguous, because you find a lot of ambiguity when you translate natural language to formal logic. Most things are not fully specified. And so a person who's an expert in the policy can use our tool to update and refine those rules to make them complete and correct. And they can do this using only natural language. They don't need to be developer, and certainly they don't need to be logicians. And once you have this, and you've iterated, you've created your automated reasoning policy. The automated reasoning policy is a resource in your AWS account. Every single change is versioned, and you can call it with a unique ARN. Configuring Bedrock Guardrail is super easy. There's literally 2 clicks. If you've tried to create Bedrock Guardrails, you know that you have all of the different configuration policies. There'll be a new one called automated reasoning. You just enable it and select the automated reasoning policy you want to use. And so with that, now let me show you a quick demo of how we go through that process in practice. Let me start the video here. And we're in the Bedrock console. You can see under safeguards, there's this new section called automated reasoning. This is where your policies go. Creating an automated reasoning policy is fairly straightforward. You just need to give it a name. You upload a document. Here, I've taken a sample HR policy off the internet. It's the kind of thing you could get probably out of your corporate internet. You upload it, and then you give the system a hint as to what you will be doing with it. Here, I just say employees will ask questions about their eligibility for leave of absence and what the benefits are, et cetera. And by the way, here's a sample Q&A. And once I click Create Policy here, the tool goes off and does the work we discussed earlier. First, we look for the important nouns, the important concepts, create a variable schema, then identify individual rules. We translate them to formal logic. We make sure that they're consistent with each other. And then we also translate them back to natural language so that the user of this tool can just operate with natural language. They don't need to understand the mathematical notation. This process takes about 4 minutes, 5 minutes. I shortened it for this video. We don't want to sit around here for 5 minutes. But once this is done, what it presents us is the structure of the policy. It shows us the list of rules that were extracted. These are not quotes from the document. This is the formal logic translated back to language, and the schema of variables. The user of this tool can add new variables, edit existing ones, same thing for rules, using only natural language. Now, you could read through all of those rules, but a good way to test it and make sure that it's correct is to use Q&A, just like your application would in production. Here, I'm giving a totally wrong answer, and this is the output you get. You see that we said it's invalid. It's invalid because it broke that rule. And this is how we translated the statement. Is full-time is false because the question said I'm a temporary contractor. And one thing I noticed is that it also said that the employee is not senior. And that's not something that the Q&A said. It probably made an assumption based on the fact that I said temporary contractor. And that, for me, is undesirable. And so I can edit that variable and be very clear, saying, hey, don't make assumptions. Levels should be explicitly stated. And then save it, and that revs another entire version of that automated reasoning policy. And as I was editing, I noticed that there was another thing in the is full-time Boolean variable. It took a quote from the policy document saying you work less than 20 hours a week, which is technically exact to the policy, but that's not how we talk about things, right? We say full-time or part-time. So I clarify that in that variable description so that it's going to be easier for us when we go to validate your Q&A to translate them from natural language to formal logic. So once I've done these 2 edits, I can go back to the test playground, run that Q&A again. In fact, I change it to check that my part-time edit worked too, and I get the expected results. Once again, it says that it's invalid. It's invalid because it broke the same rule, but it didn't make the assumption about the level. It only extracted what the claims are in the question. The fact that I'm not full-time and I want to take leave of absence. The next test is an ambiguous one. I say, I'm an employee. And the answer is, sure, go take leave of absence. That is valid. It's valid because it is a possible conclusion based on the policy. However, it's only valid if all of those assumptions hold. That list of suggestions are all unstated assumptions that your LLM needs to state for that answer to be true. And so you can take their content and use it as a feedback mechanism for the LLM. And then, like I said, using it in production is just as simple as going to Guardrail. There's a new automated reasoning entry alongside all of the other existing configurations. And you select that, you enable automated reasoning checks, select the policy, and select the version you want to use. For production, you probably want to pin it to a specific version that you've tested and are confident with. When you're testing, developing, and iterating, you just select latest so that it stays up to date. You don't have to change that configuration each time. But that's it. Once you have the guardrail configured, you can start using it in production. Now, to show you how you should think about using that feedback, I'm going to use slide rather than showing you a demo of some code because we're just all going to get lost in it. So let's go back to our example here. We have the chatbot Q&A say, can I take it off for 1 year? Sure, go. So the first thing you would do here is take this Q&A and send it off to the Apply Guardrails API for Bedrock. Obviously, you're using a guardrail you configured with automated reasoning check. And if we go back to that structure, I've kind of simplified the decision tree here and flipped it around. When automated reasoning checks looks at this Q&A, it will translate it as saying, okay, you're making the factual claim that leave of absence is allowed, that is true. And it is a possible conclusion, but you haven't quoted the constraints that are needed to reach that point in the decision tree. And that's what I meant when I said earlier, what's special about this is that we actually understand the structure of the knowledge. We don't just quote it randomly. And so if you try to feed this to the Apply Guardrails API, you're likely going to get output that looks like this. You don't need to read the whole spiel now. We're going to go through it line by line in the next slides. But starting from the top, we're saying that it's valid. It's valid because the answer, it's a literal quote from the policy. It is a possible conclusion based on the policy. However, there's a number of suggestions, and suggestions can have different types. They can be unstated assumptions, or they can be corrections. What you said is factually inaccurate. You need to change that value. And so in this case, we have 2 suggestions because you haven't quoted those constraints. And then you get an explanation, or the list of rules as you saw in the console demo, which is the natural language version of the reasoning for why something is correct or not. And so once you get this feedback from automated reasoning checks, you have a few options. You can go to your LLM, rewrite the answer. You could annotate the answer directly, or you could use it to ask clarifying questions. And we're going to go through one by one. The first one is the kind of simple one. You just take that explanation and the rules, and you create a new prompt. You feed it back to your LLM with the rest of the conversation context saying, actually, please rewrite your answer, quoting these things. That's easy, but you're making a trade-off. You're taking LLM cost, latency is just another round trip before you can show your answer to your customer. The other one is programmatically annotating the answer. You've created that automated reasoning policy in advance. It's a one-off task. And so you know the variable schema. It's a well-known thing. So you could easily, in your code, write something that says, hey, if there's an unstated assumption around level, just programmatically generate this string and append it as a footnote. There's no need to do another round trip with the LLM. It depends on how important you feel that something talks in your voice, so you want the LLM to do it, versus speed and cost. And the last one is interesting, is the clarifying questions. This is for use cases where you truly need accuracy. You want to get to an unequivocal yes, no for the user. Can I take this loan? Or, will you pay my insurance claim back? You could use that feedback to ask clarifying questions for the user. That would be the most annoying chatbot in the world, though, asking 15 questions. Or you could, more realistically take that list of suggestions and generate a form on the fly. So, yeah, I can get to your answer to yes, no, but tell me these things so that I can make that equation satisfiable and give you the final result. And there's a bunch of other ways you could use that feedback, and that's the reason why we've decided to include the feedback in the output rather than doing the rewriting of the answer ourselves. You could decide to do all sorts of things with it. And so that's the end for us here. I wanted to leave you again and repeat what our objectives are, help you build applications that are accurate, that make accurate factual claims, help you build applications that are sound. And I want you to think of soundness exactly like we do. If we can make a validity claim about something, we don't. We say we don't understand. And for use cases where accuracy matters, you should probably do the same thing. If you cannot get to an unequivocal yes, no, or these are the assumptions, you should say, please clarify, ask again, tell me a little bit more about what you're trying to do. And we want you to build applications that are transparent. We give you this auditable log of the explanation for a validation decision that you can save and keep to show if ever you need in the future. Now, I promised I was going to leave you with some next steps. I'll leave this slide up. There's a QR code that send you to links if you want to dig deeper into what automated reasoning is. That second QR code is that blog post Byron mentioned, the gentle introduction to automated reasoning. As a developer by background, that I found that blog post immensely helpful to help me wrap my head around automated reasoning. And then some more introduction to Bedrock Guardrails and automated reasoning checks. If you want to join the GitHub review, get on board, reach out to us through your AWS account teams. They know how to find me. So just send them a message and we can be in touch.